One of the most important reasons why we have a capacitor in the electrical circuit is that by storing charge on these two capacitors, on the two plates of a capacitor, the capacitor can store electrostatic energy. Okay, so let's look at how much electrostatic energy is stored on a capacitor. How do we figure that out? Well, we know if some energy gets stored on a capacitor, that is because the battery, in transporting charges from the negative plate to the positive plate, must have done some work, right? And the work done, the energy expended by the battery, then becomes the energy stored on the capacitor due to the conservation of energy. So let's look at this process. Okay, you hook this thing up, hook the parallel plate capacitor up to a battery, which supplies a terminal to terminal potential difference of V0. V0 is a fixed value. Okay, the moment you just hook them up, a current will start to flow. A flow of electrical charge will go this way. But at that moment, there is very little charge on this plate and on that plate. That means the voltage difference across these two plates is essentially zero. Now, when you deposit some charge by overcoming a very small potential difference, you don't have to do a lot of work. It's just like climbing a mountain. Okay, the mountain is this tall, and if it's not very tall, you go from here to there, you don't have to do a lot of work. But you see, as you gradually deposit more and more charges, okay, so this plate becomes more and more positively charged, that plate becomes more and more negatively charged. Then if you continue to deposit more charge, positive, onto this positive plate, you have to fight over the existing positive charges, right? In other words, from energy point of view, you have to overcome a greater potential difference. It's just like as you climb a mountain, the mountain becomes taller and taller. Okay, or you can say, we have a pile of sand, all right, and your job is to establish this pile of sand. Initially, there is not a whole lot of sand, so that you can easily put some sand on top. But as the pile of sand gets taller and taller, and then you have to put the sand all the way to the top, that takes more and more effort. So this is not a uniform process. It takes more energy to deposit a certain amount of charge dq onto the positive plate from the negative plate when the voltage gets higher. So we have to divide this into infinitesimal steps. Okay, imagine at a certain moment of time, the potential difference between these two plates is V. That V does not have to be equal to V0. In fact, eventually it will equal to V0, but that is only after everything is totally charged. At that moment, okay, I deposit a certain amount of charge dq onto this plate from that plate. Okay, I transport dq from here to there. How much work do I have to do? Does the battery have to do? Well, you know that the change in electrostatic energy for charge Q as you go through voltage difference V would be Q times V, right? In this case, dq times V. That is the increase in electrostatic energy of this amount of charge, and that of course is due to the work done by this battery. So the battery does this amount of work, dW equals V dq. Okay? But wait a minute, I know what V is. V is the voltage difference across the capacitor. The charge on that plate at that moment is positive Q, and on this plate is negative Q. So V is just Q over C, isn't it? Okay, so dW equals Q over C times dq. Now, how much total work is done by the battery? What is W equal to? Well, that would be Q over C dq, and then I have to integrate, okay? Integrate from zero charge to the final amount of charge, capital Q. And you can see that it is equal to Q squared over 2C. Okay, Q squared over 2C. I can also express this in terms of the final voltage difference across the two plates. See, when this thing is fully charged, no charge can further transport anymore. That is because this capacitor has already reached the same potential difference as this battery, so that the potential difference due to the capacitor points this way, and the battery provides a potential difference that way, and they have the equal magnitude but opposite direction, so they cancel out. So eventually you're going to reach V0. Okay, And V naught, how is it related to final charge Q? V naught is given by, Q is given by Q equals C times final potential difference V naught, right? So I can write this as C V naught squared over 2C. And that is equal to 1/2 C V naught squared. Okay, either one will give you the expression for the work done by the battery in order to establish this much charge on this plate, and by conservation of energy, this then becomes the energy stored on this capacitor. So the electrostatic energy UE stored on the capacitor can be written as 1/2 C V squared. It's also equal to 1/2 Q squared over C. That V is the amount of potential difference across the two plates, and Q is the amount of charge carried by these two plates. Okay, this is the so-called electrostatic energy stored in a capacitor. Okay, following our discussion about the electrostatic energy stored on a capacitor, let's extend this to something much more general, a much bigger topic. Now remember I said in the very first chapter, chapter 23, I mentioned, even though I didn't quite prove it, and that is the electrostatic field, the E field, is not just a working concept. It's not just defined as Q or F over Q naught being the point, test charge. Rather, it is a real physical entity with its own energy. You don't need a test charge Q naught to make sure the electric field exists. It exists on its very own, right? And how do we show that? Well, what we're going to do is we're going to borrow the special case of a parallel plate capacitor. Okay, we're going to use that example to see how we might rewrite the energy expression for a parallel plate capacitor so that it is now given in terms of the electric field in between the two plates instead of Q and V. I want to get away from Q and V. I want to establish it in the direct relationship with the electric field. And from that, we'll draw a more general conclusion. Okay, now you recall from the previous page that the charge, once the charge is given by Q on these two plates, then the electrostatic energy UE is equal to Q squared over 2C. Right? What I'm going to do is I'm going to rewrite this expression so that Q can be written in terms of electric field, and also C is just epsilon naught A over D. Remember that? Okay, because it's a parallel plate capacitor, right? So let me do that. Q is C times, first of all, I think it's easier to do it this way. Okay, I think it's easier. These are equivalent. Now let me write C now. Epsilon naught A over D. What's A? The area of each plate. D is the separation between the two. Okay, what's V? I want to write V in terms of the electric field. If the electric field, the uniform electric field between here and there is E, then it's just E times D. Right? E times D. Okay, E times D squared. Okay, let me expand this. It's E squared D squared. So I have 1/2 epsilon naught. There is an E squared. Okay, what's left is A times D. Right? A times D. Again, A is the area of each plate, and D is the distance between these two plates. So what do you think A times D is? Isn't that the volume of what? Of the region in between the two plates? And isn't that where the electric field exists? So this volume really is the volume in which the electric field E exists. Now move that volume down over here. Electrostatic energy. Electrostatic energy, which in this case it's just UE, right? You divide this by volume, which contains this energy. That is, of course, called energy density, or electrostatic energy density. Okay, we use the letter lowercase UE to denote it. How much is that equal to according to this expression? At least for a parallel plate capacitor, how much is that equal to? move that over, is just equal to 1/2 epsilon naught E squared, isn't it? Right? Okay, so for this particular special case, for this simple geometry of a parallel plate capacitor, we learned that energy, the electrostatic energy stored per unit volume in this region is 1/2 epsilon naught E squared. So you see, you have the electric field somewhere in between. You will establish an energy in that region. Of course, you can say, well, this is only for that special case. What if it's a spherical conductor? What if it's anything different? Well, we're not going to show it here because the math goes out of our reach for Physics 1C. But I can tell you, okay, I can tell you that the result applies to any electric field of any distribution. Okay? And it says that whatever the electric field is, as long as in a certain region in space there is an electric field, then this region also acquires an additional amount of energy in association with this electric field. And the energy density, in other words, energy per unit volume, is always equal to 1/2 epsilon naught E squared. One can show that from the most general equations governing the electromagnetic field. So this is what we did here because of the limit in the mass tool that we have available. We did it with a special case, but you can show that this is actually valid for the most general case. In other words, wherever there's an electric field, there's always an energy in this region surrounding it. And energy, as you know, is something real. In fact, according to Einstein's theory of special relativity, energy is directly related to mass. Okay? So wherever there is energy, there is also mass associated with it. And mass, as you know, you cannot get anything more real than mass. When you have something has a mass, it must exist. It must be a real entity, right? So, in principle, if you bring a charge to a certain region, that charge, you can not only feel it by putting another charge to see if there's a force between them, but the very existence of the first charge would establish an electric field which brings a certain amount of energy per unit volume to the surrounding of that charge, and that energy surrounding the charge also carries its own mass. So you basically have changed the mass, okay, of the space around it by establishing an electric field. And of course, mass is very real, and therefore the electric field is very real. You do not need a second test charge to for the electric field to exist. It exists on its own. It can actually also propagate in a waveform from one part of the space into another, and we'll learn that later in a so-called electromagnetic wave. So the electric field is a real entity. We see that from this energy expression.